Okay, we are going to talk about section 6, related rates. This is the second major type of word problem that we're going to deal with. We're going to spend several days on it. So let's get right into it. Very similar to optimization. With related rates, we are going to have, we're going to kind of follow a series of steps, call them steps to greatness. And if you do this, especially for related rates, but also for optimization, but really for related rates, these steps are really helpful, I think. So step one, draw and label a diagram. And you want to keep your diagram as general as you can. And if you decide to put in values um, for different parts of the diagram, you only want to put in values for things that are not changing. Okay, so we'll talk more about that in the examples, but you want to generally keep it as general as you can. Find a model for the situation. That's a mathematical model. Okay, that usually relates all of the parts of the diagram. Take the derivative. Write down everything you know, and I'll show you what that means in a second. Plug in all of your known values. If you have more than one variable at this point, you've made a mistake. Go back to step one, and then you're going to solve for the unknown variable and then state your solution in the context of the problem. This is different than optimization. The derivative will be necessary. Calculus will be necessary in these problems. Optimization, you could get away with graphing. We talked about how some of them were very similar to pre-calc type problems, but not so much in this section. Okay, so let's start with the first example here. Suppose I have a perfectly spherical balloon. When I blow up the balloon, what two things are changing? So maybe you pause it here and think about it. Maybe jot down what two things are changing. There's a number of things. If you pause, you should have probably a couple of these things. Volume is changing. Surface area. Area is changing. The radius is changing. The diameter is changing. Okay, so there's a series of things that are changing as this balloon expands. And let's make that stop doing that. Okay, so let's find an equation that relates to things that are changing. Now, the problem that we're going to deal with is ultimately going to be using volume. So we will relate volume, and then the volume of a sphere, the formula, has radius in it. So I suppose we could change it for diameter, but it kind of by default, the formula that we use most frequently has radius in it. So the model here would be v equals 4/3 pi r cubed. Okay, so we're relating volume and radius. Both things are changing as we blow up the balloon. Air is being pumped in. So here's the actual example then. Air is being pumped into a spherical balloon at a rate of 10 cubic centimeters per minute. Determine the rate at which the radius of the balloon is increasing when the diameter of the balloon is 15 centimeters. Okay, so let's just go right through the steps here. Step one, we need a picture of what's going on. So it's going to be a spherical balloon. So we'll go with a circle here. Make it look somewhat like a sphere. This distance here will be our radius. And actually the volume is just dependent on the radius. And so that's really the only thing we need to sketch in there. We're keeping it as general as possible, and just with the one thing that we're paying attention to, R, just leaving it as R. Step two, find a model. Okay, well, we already got that. We sort of did a lead up into this one, right? So v equals 4/3 pi r squared is the model. Let's draw a line here. So then step three says take the derivative of your model. Okay, so I've got the model here. Now this is where we're going to use actually implicit differentiation, because r is changing as well as v in the situation. So so we are going to build that in when we take the derivative. Let me show you what I mean. So the derivative of v with respect to t, let me pause for a second here. You might think, well, so what? X is changing when we take the derivative of y equals x squared. X could take on any value. But what we're going to do is we're going to derive with respect to t. So we're actually taking the derivative with respect to t of both sides, d dt. Because ultimately we want to know how fast the radius is changing. So we want change in radius with respect to time, dr dt, at the end. So we're going to derive both sides with respect to t. Therefore, r is not our independent variable. Time is, t is. Okay, so that's why So that's how we're going to derive this. That's why we're not going to treat r as the independent variable. So when I take the derivative, I will get dv dt. That's going to be equal to 4 pi r squared times dr dt. We're thinking implicit differentiation here because we're deriving r with respect to time. So we need to use implicit differentiation. Step 4. Step 4 is write down everything you know. Okay, so I know a few things. I'm given that the air is being pumped into the balloon at a rate of 10 cubic centimeters per minute. So I'm given this, that dv dt is equal to 10. All right. I'm also told that I want to know how fast the radius is increasing. When the diameter is 30, that means when the radius is 15. So when r is 15, and then I want to know dr dt, ultimately, the change in radius with respect to time. I don't know that. Okay. And then we check. We make sure that there's only one variable. There is, right? I'm going to fill in this one, this, and then I'll be left with trying to solve for dr dt. So step 5 is plug everything in. So I'm going to have 10 equals 4 pi 15 squared dr dt. Okay, and then the last step is actually solve it. So when you actually do the math out, you get that it's 0.0035 centimeters per minute. All right, and hopefully it makes sense that when the balloon is really small, and you're just pumping the same amount of air in all the time. When the balloon is small, that radius grows really fast, right? But when the balloon is really big, the radius is going to grow much slower. Okay, so that's the type of problem we're going to deal with, is where we've got multiple things changing. Calculus can help us deal with all of those rates in one instance. So in this one, we have dv dt happens to be constant, but we can figure out what dr dt is at a given instant, despite the fact that it's changing as the balloon gets bigger. Okay, next one. Police car is approaching a right-angled intersection, chasing a speeding car that has already turned the corner and is heading straight east. When the police car is 0.6 miles north of the intersection and the car is 0.8 miles east, the distance between the cars is changing at a rate of 20 miles per hour. If the police car is going 60 miles per hour, how fast is the other car going? Hint, the police car is moving in the negative y direction. So here's what we've got going on. We have a car heading, the police car heading south, and then another car is heading east, the car that's being chased. And so here's our roadway, I guess. So let's say that this point right here is the police car, and then out here somewhere is the car that the police car is chasing. So we're in step 1 here, right? Step 1, we're trying to label and create a diagram. So we know that the car is going this way. That's going to be the positive x direction. The police car is going this way. That's in the negative x direction. Sorry, negative y direction. So I think it makes sense to label x this distance here and y this distance. Usually if you can just keep it in concert with the xy plane, that's a good idea. All right. So, and then this distance here from the cars, we know, we have information about that, right? We're told that that rate is changing at 20 miles per hour, so we should label that, call that z. Okay, so now that I've got my model sketched out very generally here, right? I didn't take any of these values and I didn't plug them in yet. I'm going to go get my model. So my model that relates x, y, and z, all the things that are relevant and changing, is just going to be the Pythagorean theorem. X squared plus y squared equals z squared. Okay. Now, for step 3, we're going to take and do the derivative, right? And we're taking the derivative with respect to time, so all of this is going to be, all of these are going to require implicit differentiation. So I will get this for step 3. 2x dx dt plus 2y dy dt 2z dz dt. Okay. Step 4. Write down everything that we know. Oh, actually, one thing that I'm going to do that I guess I should have showed out. You can divide everything by 2 here, and all the 2's will drop out. So when we actually go to solve the problem, I'm not going to write the 2's down. And you don't have to do that, but it just makes it a little bit simpler. So let's write down everything we know. We know what x is. X is going to be 0.8 because that is how far the car is miles east of the intersection. So this is going to be 0.8. We don't know dx dt. Dx dt would be how fast the car is going. That's unknown. This is a good point, a good place to pause and see if you can write down everything and maybe just see if you can finish out the problem. See how you do. After pausing the video. We also know that the police car is 0.6 miles north of the intersection. So that's 0.6 miles for y. dy dt, we know that is 60. 60 miles per hour is how fast the car is going. And it's a negative 60. Although I didn't write down negative 60. Why didn't I? I'm going to leave it at 60. Here, although it's moving in the negative direction, so I feel like it should be. Anyway. And then z. I don't know that distance, but I can figure it out, and I will do that in a second. dz dt, that's how fast the distance is changing between the cars. And so dz dt is going to be 20. And then I can figure out what z is. So I don't know, it's not given to me in the problem, but if I know that x is 0.6 and I know that, x is 0.8 and I know that y is 0.6, I can use the Pythagorean theorem. If I do that, I'll figure out that z is 1 mile. Okay, is the distance for z. So now I can go on to step 5. In step 5, I'm going to plug in everything that I know into the equation and then solve. So I will get 0.8 for x times dx dt plus 0.6 for y. Again, I'm dropping the 2's out because the 2's drop out. So 0.6 for y times dy dt. Okay, yes, we need this to be negative 60. So because he's moving in the negative direction. And then that's going to be equal to 20 times 1, or 1.0 miles times 20. When you solve that out then, you end up with step 6, which is dx dt is equal to 70 miles per hour. Okay. So again, that's because the police car is moving in the negative direction. So the distance, so the car is actually moving 70 miles per hour then. All right, let's move on to the next one. A hot air balloon is rising straight up from a level field. It's tracked by a rangefinder 500 feet from where the lift point is. Okay, so let's sketch that out. So what we have is a person, let's presume, is standing 500 feet from where a balloon is taking off. It goes up for a while. The rangefinder's elevation angle is pi over 4. The angle is increasing at a rate of 0.14 radians per minute. So that's pi over 4 radians. How fast is the balloon rising? So this is the situation. We've got a rangefinder over here. The balloon is going up. Here's where the balloon is at the instant that we want to figure out how fast it's rising. We've got a right angle here. We're going to call this angle theta because that distance is changing, and the height of the balloon, we'll just label that h. Again, that distance is changing. We can actually label this distance as 500 because that's unchanging. That's not going to matter where the balloon is. That's going to be 500 feet. So there's our step 1, getting a picture. Now we want a relationship between all of the relevant variables. So I've got theta, h, and 500. So that relative to theta, this is the opposite side of the right triangle. This is the adjacent side. So opposite over adjacent is tangent. So for step 2, our mathematical model will be tangent of theta is equal to h over 500. Like that. So there's our model. Step 3 is take the derivative. So when we derive tangent, we'll get secant squared theta times d theta dt, which is equal to, this will just be 1 over 500 times dh dt. Step 4. Write down everything you know. We know that theta, the angle at the instant, that is pi over 4. It's a bad 4. Pi over 4. We know that d theta dt is 0.14 radians per minute, so 0.14. And then we want to know what dh dt is. Okay, so we plug everything in for step 5 and solve. So I get this, secant squared of pi over 4 times 0.14 is equal to 1 over 500 times dH dt. You're going to solve that out. And then for step 6, you should get that dH dt is 140. And then you want to make sure your units are right. So our distances have been in feet and our time has been in minutes, or as well as in radians per minute. So it's 140 feet per minute for your final answer. Okay, again, everything is in the positive direction here, right? This is increasing in the positive y direction. Theta is also increasing, so we would expect the theta dt in our answer to both be positive, right? And that sums up part 1. I think we're going to stop here. We'll do a part 2 video for the other 2 examples that are a little bit more involved. And hopefully from that you can kind of see the pattern. We're going to follow those steps every time, and they really, if you follow those steps, usually these problems are manageable. Okay? So, I'll see you in the part 2 video.